is an electronics enclosure and my first attempt at making it. Honestly, I have avoided anything mechanical my whole life because I'm just so much more comfortable with electronics and software. So in today's video, I will narrate over an actual screencast that I took while making this case. This is, I know, has been a very long video, but I hope the chapter links down below will help you hop around to wherever or whichever feature you want to look at. And some of the chapters will actually show how I fixed my mistake and go about tweaking my design, because guess what? That is the actual process of making things. So before we get into KiCad and FreeCAD, it helps to look around for inspiration, and there's plenty on the internet. On the Thingiverse platform, we can browse many designs and download the STL file for 3D printing. I also made a collection of electronics enclosures just to get a feel of how 3D printed cases look like and get some ideas for my design. Apart from online ideas, maybe you have some electronics enclosures or 3D printed cases at your home or work. For example, this open scope case by Digiland also has a Thingiverse link to download all the STL files. Luckily, I could use this 3D printed case to do some manual measurements and refer those numbers in my design. So having a vernier calipers and a ruler can come in really handy, and also keep your bill of materials ready with all the data sheets of your components, because we will keep referring to the mechanical sections for the measurements. And finally, we come to the software, KiCad and FreeCAD. I will be using KiCad version 6.0 to do some measurements and export the 3D models of the entire populated PCB. And FreeCAD, I want to thank the friendly CAD YouTubers like Flowy from FreeCAD Academy on the 3-part series on FreeCAD and Adventures in Creation on parametric design of an enclosure. I referred to these videos first before making mine. So go ahead and download the latest version 0.20. I'm using a slightly older version 0.19, but it shouldn't matter. Pair this up with the super helpful wiki site of FreeCAD, and I kept referring to it for all kinds of icons and what they mean. Initially, I was intimidated by all the icons when I first opened them, so I will show the enlarged icons at the bottom right-hand corner while using the function. Right clicks will be red in color and left clicks will be blue in color so that we can all see clearly when I make those pointer clicks. I think that's about it, so let's get started. For the first step, we will create a simple cuboid and save it as a new document. Open FreeCAD, go to File, New. In the combo view on the left sidebar, click on the Model tab. The drop-down menu at the top shows a list of all the installed workbenches. Choose the part workbench. Then choose the yellow icon to create a new part and make it active. I always right-click and rename it immediately so it's easy to reference later. I named it as Oak Case. Next, choose the part design workbench and click the icon to create a new body under the part. Right-click and rename it as well. With the new body selected, click the icon to create a new sketch. This will present us with a menu to create the sketch on either of the 3 planes. Choose the first one, XY plane. And now we are ready to sketch. So we have a part and then a body underneath and then a sketch underneath. I know at this point of time it might feel very redundant, but trust me, this clear nested structure with descriptive names really helped me debug later on, especially as the design got more and more complicated. So hang in there with me. Inside the sketcher, click the icon to create a rectangle. It doesn't really matter where you place the rectangle because now there are 4 degrees of freedom that we have to solve. First, click the length of the rectangle and then the icon to define the horizontal distance. For now, any length will do, so just put 60 millimeters. Similarly, click the width of the rectangle and then the icon to define the vertical distance. For example, 30 millimeters. And finally, click the origin and the bottom left corner of the rectangle to make it a same point by clicking the coincident constraint. Now that the sketch is fully constrained, click the close button. Have a feel of rotating and zooming with your mouse and clicks. At the bottom right-hand corner, hover over the mouse icon and you will see explanations on basic select, zoom, rotate, and pan, or click the mouse icon and choose your preferred navigation style. I chose the CAD style. Next, to give the sketch some height, select the sketch and click on the pad icon. A dialog will open up where we can put in the length. Once again, it doesn't matter what the length is for now, so I just put 15 millimeters and click OK. And we have created a simple cuboid in 3 dimensions. To save the document, hit Ctrl S or Command S and name it, for example, case. Until now, all the dimensions were hard-coded, for example, 60 millimeter or 30 millimeters. But this becomes very troublesome once we have to change that 60 millimeter in so many places. In computer science, we solve this with variables and functions. In computer-aided design, we solve this with something very similar called the parametric design, where features are shaped according to algorithmic processes. In FreeCAD, we do that by defining all the parameters in a spreadsheet and then using them in an equation to calculate all dimensions. To start a parametric design, change the workbench to spreadsheet. Every time I create something new, I always ensure it is nested under the part case by dragging it in. Then start naming these parameters like PCB_length and PCB_width. And where do we get the dimensions from? It's from KiCad or your electronics design software. In the PCB editor of KiCad, I always use the user drawings layer to mark any measurements. Also make sure you change the grid to something in metric 1 millimeter. Next, click the ruler icon and measure the width of the PCB, which is about 40 millimeters, and the length at 100 millimeters. Come back to FreeCAD and put these dimensions in the spreadsheet. But we need to tell the software that the numbers in column B correspond to the names in column A. To do that, right-click the number, go to Properties, click the Alias tab, add in the exact name from column A, and click OK. The number cell in column B will turn yellow to indicate that it has an aliased name. So imagine now you have a long list of names and dimensions. It will take too much time to alias them one by one. That's why we can use something called macro in FreeCAD. And this particular case, there is a macro called Easy Alias that takes text labels already created in one column and uses those labels as aliases in the next column. And to install it, go to Tools, Add-on Manager, tab Macros, scroll down the alphabetical order, find Easy Alias, and click Install. Once it's installed, select all the parameter names in column A, go to the menu Macro, Recent Macros, and choose Easy Alias. All the cells in column B are now aliased with the yellow color. If we go to a newly aliased number cell and right-click its property under the alias, we will see the parameter name from column A. Now comes the fun part. We got to use these newly defined parameters in the cuboid that we created. So double-click the sketch in the sidebar and click the length of 60 millimeters. To use the parametric names, click the little blue circle on the right of the text box. Now we can use spreadsheet values by typing in spreadsheet dot and selecting the drop-down menu of aliased names, for example, PCB length. Click OK, and the length is now defined as 100 millimeters, but it is actually whatever the parameter PCB length contains. Do the same with the width. Click the vertical distance, click the blue circle, type in spreadsheet.pcb and choose from the drop-down menu PCB_width. Now the cuboid has parametrically defined length and width. When designing a complete enclosure, which is 3-dimensional, it is not as easy as just putting in the length, breadth, and the width. So I added a few more parameters such as wall thickness of the enclosure, clearance between the wall, and then the start of the PCB. Sometimes I had to get the vernier calipers to do the actual measurements such as the wire bending portion or the height of the PCB from the bottom. Because this is my first enclosure, I designed the case after my PCB, but I don't think this will be the case for my future designs. I mean, for example, look at this Digilent OpenScope PCB. This was obviously designed side by side with an enclosure in mind. So I added these extra dimensions into the spreadsheet and aliased them. To use these new dimensions, go back to the sketch and click the length of the rectangle and define it in an equation which is wall thickness times 2 on both sides, clearance times 2 on both sides, plus the PCB length and the wire bending. Similarly for the width, wall thickness times 2, clearance times 2, plus the PCB width. Close the sketch and click the pad of the sketch to define the height. We can either double click the pad or come down in the sidebar to edit the length. The equation this time is also wall thickness times 2, clearance times 2, plus the electronics height. One final touch. We will add some fillets to the sharp edges. To do that, change to the Part Design workbench, select one of the edges, and click the fillet icon. A dialog will open up showing edge 5 as the edge having a fillet of radius 1 mm. Click the Add button and then another edge. Repeat the process until all 4 edges are selected and then click OK. We now have a parametric cuboid with fillets on the edges. Now that we have a rough cuboid to hold the entire electronics, we should prepare to export the 3D model of the PCB from KiCad into FreeCAD. So we will learn how to associate one footprint with one 3D model of the component, but we can make it better by adding more 3D models. First, do ensure the paths to the 3D models are correct by going to Preferences and Configure Paths. Associate a 3D model by selecting a component, for example, a resistor, and hit the E key for footprint properties. Tab 3D models and choose the 3D model, usually from KiCad's own library. Sometimes a 3D model might not be available in the library. For example, this side push button. GrabCAD is another useful website where such 3D model step files are available for download. I found one that matches perfectly the push button. I downloaded and added it to the 3D model for the associated footprint. Let's look at this antenna, which already has a 3D model for its SMA connector, but wouldn't it be more accurate to also add the stub antenna? To associate another 3D model, click the plus sign and add another step file. Play around with the scale, rotation, and offset until you have the antenna in the right position. Now, when we go to the 3D viewer, the antenna footprint has two 3D models, the SMA connector and the stub antenna. I did something very similar with the e-ink screen, which initially had the right angle header prints just for the electrical connections. But I added 4 hex nuts and the e-ink screen to give it a much more accurate picture. So we don't have to restrict ourselves to adding one 3D model to one footprint. Go ahead and add more 3D models like this 18650 battery holder and the battery. One last step before we import the PCB into FreeCAD. The origins of both the PCB as well as the case must be the same. In FreeCAD, the origin is set to the bottom left-hand corner of the rectangular case. In KiCad, go to Menu, Place, Grid Origin to put a marker at the bottom left-hand corner as well. Ensure the grid size is set to 1 mm or whatever is accurate in your design. Because this is my first case, I actually designed it twice. And the second time around, I am so glad I imported the KiCad model this early in my design process. We need a new workbench for this. So go to Tools, Add-on Manager, tab Workbenches, scroll down, choose KiCad Step Up Mod and click Install. This is one of the ways of installing it, but somehow it never worked for me, so I tried the other method listed on the GitHub, which is to manually copy the folder to the mod subdirectory of FreeCAD. You can also copy the Git URL, go to the mod directory, and git clone the repository. And after restarting FreeCAD, KiCad Step Up is found in the drop-down list of workbenches. So click the Import KiCad PCB board and parts icon. Navigate to the file.kicad_PCB and click Open. Immediately, the entire PCB with the 3D models can be seen inside FreeCAD. I had another error with all the 3D models scaled in KiCad. I never figured out how to solve this error, so I was a little cautious of those parts, such as the antenna, the push button, and the battery. The imported PCB board will eventually have many bodies nested under one part. To keep things organized, rename the part immediately to something like the project name and PCB, and drag it inside the current document. Close the other newly created document without saving it. So now we have one document with two parts, the case and the PCB. Initially, the PCB traces will be missing, but I love to see them. So click the Add Tracks icon to render this visual. Press the spacebar to see the case together with the PCB. But to see things through the case, right-click on the body case, choose Appearance, and increase the transparency to about 40%. Next, we have to align it a little bit, so click the top of the navigation cube at the top right-hand corner and zoom into the origin. Because we made sure the origins in FreeCAD and KiCad are at the same point, the board aligns perfectly. But we need to add the clearance and the wall thickness. Come to the bottom of the sidebar under Placement, Position X, click the spreadsheet blue circle. Move the PCB slightly in the X direction with the equation wall thickness plus clearance. Copy-paste the same equation for position Y. We are left with position Z. This time, the equation will be wall thickness plus clearance plus PCB height from the bottom. And we are ready to add more details to the case. Next, we will create some connector slots so that we have access to them. For example, this slide switch needs an opening to access it. And I always start with a new feature by adding the dimensions to the spreadsheet, such as depth, height, width, and offsets. Many of the offsets can be measured in KiCad again, for example, 9 millimeters for the Y offset. For the rest, refer to the datasheet where the mechanical dimensions are drawn. For the width, it's about 6.7 plus 1, 7.7 millimeters. The depth is 4.1 millimeters and the height is 1.4 millimeters. I also have some common dimensions like connector clearance and extending in and out. In the final step, run the easy alias macro. Come back to the part design workbench, make sure the part case is active, create a new body underneath it, and rename it to something descriptive such as switch on off. Then create a sketch underneath the body in the XY plane. We are ready to create a connector slot. Now I know connector slots can come in many designs, but because this was my first case, I decided to go something very simple, cuboid shape, because done is better than perfect. Later on, we will make a Boolean cut of this cuboid shape from the entire case, and that's why I am using the extend in and extend out dimensions to ensure they protrude out for a clean cut later on. So start by creating a rectangle roughly around the component. If the PCB gets in the view, click the View Section button to temporarily hide it. With 4 degrees of freedom, let's add constraints to the sketch. First, click the horizontal dimension of the rectangle and click the horizontal distance icon to set the equation of extending in and out plus the depth of the switch. Next, click the origin and the nearest point and click the horizontal horizontal distance icon to add the extend out dimension because we will later do a clean Boolean cut of this connector slot. Similarly, click the vertical dimension to set a vertical distance of the connector clearance on both sides plus the switch width. And finally, click the origin and the nearest point again and click the vertical distance to set it as wall thickness plus clearance plus Y offset. With a fully constrained sketch, close the sketcher. The little rectangle can be seen right at the bottom. To pull it up to the switch, select the switch body, come down in the sidebar, placement, position Z, and add the equation of wall thickness plus clearance plus PCB height from the bottom. Oh no, I keep making the same mistake in the equation. Maybe clearance and connector clearance names are too close. But anyway, the sketch is way too near the switch. So we now need to minus the connector clearance. Now that we have the base of the slot, select the sketch again and click the pad icon. As usual, click the blue circle to add the equation of connector clearance on both sides plus the height of the switch. To see things a little better, right-click the switch body and then select a random color. And right-click again to change the appearance so that the transparency is about 40%. With a slight change in the appearance, it is very clear that the slot does not really cover the entire switch. Maybe we can look into the Y offset equation again. So double-click the sketch again and double-click Y offset dimension to check the equation. Yep, I forgot to minus the connector clearance. That looks much better now. So I did something very similar with other connectors like the push button, the antenna, and the micro USB connector. But for the e-ink screen, I wanted a rounded rectangle. So click the constrained preserving sketch fillet icon and two sides of the rectangle until all have rounded corners. Click the four rounded corners and then the equal sign to make them similar in dimension. And to set the radius of these rounded corners, I visited the mechanical drawings of the e-ink screen and saw that it is 2.5 millimeters. Back in FreeCAD, select one of the rounded corners and then constrain the radius to slightly bigger 3 millimeters. I hard-coded this, but maybe I should have also put it in the spreadsheet, and the rest of the steps are very similar. Lastly, I wanted circular LED slots like the ones inspired by the open scope. I have a couple in my design for the charging LED and the GPS pulse per second LED. After measuring the offsets from KiCad and aliasing them in FreeCAD under a new body, draw a circle. Constrain the diameter to LED diameter, which is defined in the spreadsheet. The rest of the process is the same, except when you pad it, check the symmetric to plane option so that it will extend in and out equally from the top of the case. Next, we will create the bodies for ventilation holes, but because they are in a repeated pattern, we will create them with something called arrays. As usual, start by adding some dimensions to the spreadsheet and alias them. Create a new body and rename it vent hole singular. Create a sketch under it in the XY plane. Start by creating an arc with a center and endpoints. One side coincides with the origin and the other side is on the y-axis. Join it with a line and another arc at the other end. Complete the slot design with a final line. With 4 degrees of freedom to solve, let's constrain the sketch. Select the 3 points of the arc and give it a vertical constraint. Select both the arcs and make them equal. Constrain the diameter of the arc to the vent hole width parameter. And finally, the horizontal distance is vent hole length. With a fully constrained sketch, we are ready to create multiples of it. Clear the view by disabling all the other connector slots with the spacebar. Select the sketch of the single vent hole and add padding by checking symmetric to plane with the dimension of extend in and extend out. To access the array feature, change to the draft workbench. Click the array icon and a sidebar will open up. To be honest, I hardly used this sidebar because I couldn't find the blue spreadsheet icon, so it doesn't really matter. Close it. As usual, keep things organized by dragging the created array under the part case and renaming it as vent holes plural. At the bottom of the sidebar under the orthogonal array is where I start by playing with the interval XYZ and numbers XYZ. It's pretty fun to see them multiply in real time, and to move them from the origin, change the X and Y coordinates under the placement position X and Y. I never needed to touch any Z numbers because the ventilation holes are only at the base of the enclosure. In the end, I used the X in the interval X, Y in interval Y, all zeros in interval Z, and 3 of them repeating in the X direction, 10 in the Y direction, and 1 in the Z direction. As for the placement, I shifted them in the X and Y direction, but nothing in the Z direction. With the spacebar, turn on the views of all the slots created so far and the PCB. We are ready to finally cut the holes and the enclosure. Make the case active by double-clicking. Click on the Tasks tab and click on Boolean operations. But I decided to turn off the PCB view with the spacebar and go back inside the Task tab. Click Add Body and click one connector slot. And repeat this process until all of the bodies are chosen except for the ventilation holes, which is an array. In the drop-down below, choose Cut as the type of Boolean operation. This is where I really appreciated naming things properly, as I could see an entire list of descriptive names. Hit OK and we have all the slots created. Turn on the view of the PCB to take a real close look at all the openings. Next, we choose the case and the array of the ventilation holes. Change to Part Workbench and click the icon to make a cut of 2 shapes. The vent holes are now cut. I always have this warning at the bottom on links going out of the allowed scope. Maybe it's something to do with the nested structure. As always, to keep things organized, drag the newly created cut object into the part case. Now we will create the internal box for the enclosure. So change to Part Design Workbench. Create a new body, rename it to enclosure, and create a new sketch underneath it in the XY plane. Let's start by creating a simple rectangle. With 4 degrees of freedom, select the horizontal distance and constrain it to, in my case, the PCB length plus the wire bending portion. And constrain the vertical distance to PCB width. Choose the origin and the corner of the internal box and constrain the horizontal distance to wall thickness and clearance. Add the same equation to the vertical distance. Close the sketch and maybe disable the external box view with the spacebar. Let's pad the sketch with just electronics height. To see things through, enable the view of the external box, right-click Appearance and increase the transparency. And do the same with the internal box. Right-click, add a random color, and right-click Appearance to increase the transparency as well. Now we should be able to see the internal and external boxes clearly. You can immediately notice that the boxes are not aligned properly because the wall thickness is not uniform all around. Something is wrong. Let's get debugging. Go to the internal boxes sketch and check the dimensions. So the distance between the external and internal boxes should just be the wall thickness as 1 millimeter. So I changed both the vertical and horizontal separation distances. Hence, the length of the internal box must add clearances on both sides now. The same goes for the vertical distance, where I added clearance times 2. Then I expanded the cut Boolean operation and found the old case had operation and the sketch underneath it. I inspected the horizontal distance and found the mistake. It should have been clearance times 2 instead of connector clearance. I made the same mistake with the vertical distance. I fixed the equation and it looked a lot better. Now I was ready to cut the internal box. Change the workbench to part. I realized the internal box was not raised at the correct wall thickness, so I selected it and changed the Z position under placement in the sidebar to adjust the wall thickness. Then select both the internal and external boxes, choose the icon to make a cut of 2 shapes, and finally, to keep things organized, move the newly created cut object back into the part case. We have finally created the enclosure with the correct slots and openings, change the transparency and the color, maybe rename it as well, turn back the PCB for the view. To hold the case together, we will create an external screw lug. Click the spreadsheet in the sidebar and some related dimensions such as the screw diameter and the screw lug's diameter. Be sure to run the easy alias macro again to alias their numbers with the names. Next, double-click the part case to make it active. Create a body underneath it. Rename it as screw lug and create a new sketch for the body in the XY plane. Start with 2 circles whose center is on the y-axis. Then click the arc to create the sides of the screw lug. One end of the arc touches the x-axis while the other end touches the circle, and we do the same on the other side. And lastly, with the line tool, draw the vertical, horizontal, and another vertical line to connect it all up. With 12 degrees of freedom, let's constrain the sketch. Add a vertical constraint to the side. Click the arc and the circle to give it a tangent constraint. And do the same with the other arc. Click the internal circle to constrain the diameter to the screw diameter. Click the external circle to constrain the diameter to the screw lug diameter. Seems like we need to give a vertical constraint to the other side as well. Give a dimension for the horizontal distance. I did not link it to the spreadsheet so that I can amend it for each screw lug if it clashes with other features. And the height of the screw lug edge will be the wall thickness, as we will fuse this part with the wall. With 4 degrees of freedom left, select the tangent points and the center of the circle to give it a horizontal constraint. Click the 2 arcs to make them equal, and finally there's 1 degree of freedom in the vertical distance. So give it a dimension of 4.3 millimeters. With a fully constrained sketch, trim the internal lines so that there are only lines on the edges of the sketch, else there will be errors later on when we try to pad it. We are ready to give it a height. Select the sketch, click the pad icon and change the length equation to wall thickness times 2 plus clearance times 2 plus the entire height of the electronics. Move the screw lug from the origin by editing its properties at the sidebar. Placement position X at 6.5 millimeters. Once again, tilt and check that it does not block any connector slots. Next, we will create copies of the same screw lug and position it externally to hold the case or internally to hold the PCB. To copy, right-click the first screw lug and a dialog will pop up for object selection. We will copy everything from the first screw lug except for the spreadsheet, so uncheck it. To paste, right-click the case and click Paste. Drag the newly created screw lug inside the part case to keep things organized. Create the third and the fourth screw lugs, but we can also copy and paste with the shortcuts Ctrl or Command C and then Ctrl or Command V. Once again, drag them all inside the parent part case. Right-click the second screw lug, click Transform, and use the red arrow to pull it along the x-axis. Similarly, use the blue ball to rotate it 180 degrees. At this point, I just want to place the 4 screw lugs approximately at their final positions so that I can see them individually. After the coarse adjustments, we are ready for the fine adjustments with parametric design. Click the second screw lug, come down in the sidebar property, placement position X, and put the equation for the entire length of the case, which is the wall thickness times 2, clearance times 2 plus PCB length, and the wire bending portion, and then minus 6.5 like the first screw lug. And the screw lug will move in the exact position. Thanks to parametric design, we can cut and paste the equation for the X direction for the third screw lug. And for the Y direction, the equation will also be wall thickness times 2, clearance times 2, plus the width of the PCB. And click, it will snap accurately to the exact position. The final screw lug is easy because we can copy and paste the equations. As always, change the appearance, turn up the transparency, rotate it around to have a good look, and ensure the screw lugs are not blocking other features. I already made a couple of M3 holes in the PCB and I want to hold it in place with internal screw lugs. So start by copying the original screw lug 2 more times with coarse and fine adjustments just like before. But this time we will notice the internal screw lugs have a lot of clashes with either the PCB itself or other connector slots such as the antenna and the micro USB. So let's tweak and adjust. Find the body of the internal screw lug and the pad length in the sidebar property. Reading equations with descriptive names from the spreadsheet makes things so much easier. Instead of adding the entire electronics height, it will just be the PCB height from the bottom. Okay, so it already looks better, but can we improve it further by subtracting the connector clearance? I don't know what I was doing. The PCB is hanging in the air. Anyway, I fixed the height of the second internal screw lug by adjusting the length of the pad as well. By this time, it was still clashing with the antenna connector slot, so I had to now get to the sketch to tweak it further. Click the View section icon to clear up the view in the sketch. Double-click the horizontal distance and reduce it by a little bit to make it 9 millimeters. And now it does not clash with the slot anymore, but the PCBs are still hanging in the air. So I decided to hunt down the original connector slot and reduce its height. To do that, I had to dig inside the nested structure. This is where I really appreciated having clear descriptive names. To change the Z position of the slot, select the micro USB slot body, come down to the sidebar property placement position Z and remove the connector clearance at the bottom. Next, choose the pad length in the sidebar, increase the height, and add the connector clearance. No more clashes. Edit the other screw lug to ensure it also has the same height that reaches the PCB. Finally, just to check things, change the transparency of the case, maybe turn off the PCB visibility with the space bar, and take a close look at all the screw lugs to ensure they are not obstructing other features. Next, we will add some battery supports to hold up the PCB. The shape is so much easier than the screw lugs. We just need to check the data sheet to ensure the dimensions are correct. So I noted down the length and the width of the battery holder. Ensure they are also in the spreadsheet along with the usual X and Y offsets that you can measure from KiCad. Alias all the dimensions and all the cells should be highlighted in yellow. Start with a simple rectangle, padded, copy it again and adjust their positions. And most importantly, check they are actually supporting the PCB without any clashes. Maybe turn off the screw lugs or the PCB for a clearer view. Basically, very similar steps to the screw lugs. Now comes the exciting part. We are going to fuse 4 external screw lugs, 2 internal screw lugs, and 2 battery supports, plus the case. Just counting and appreciating my nested structure so far. To fuse all of these features, change to Part Workbench. Select all the 9 features and click the icon to make a union of several shapes. A new fusion will be created, and as usual, I drag it inside the part case. And finally, after changing colors and transparency, we should see a clean case with all the fused features. Maybe turn on the PCB's visibility with the space bar to check everything is fine. The final feature is to add text. Once again, I got inspired by the open scope case where they had the text for the project name and helpful LED names with these rounded slots. The text is also embedded into the case wall, so it is very smooth to touch. As usual, start with some dimensions in the spreadsheet, such as the font height and the text extrude. Did I mention we can also add readable equations into the cells? For example, wall thickness divided by 2. Alias all the cells, and we are ready to add the text. Change to the draft workbench and click the shape string tool. In the sidebar, the properties of the text to create will open up. Click with the crossbar on an appropriate position to set the X and Y coordinates of the text. Change the string field to CH to mean charging LED. Change the height, but it does not matter now. We will link to the spreadsheet value later. And finally, navigate to a font file on your computer. With these parameters set, click OK. We should see the text created right at the bottom of the case where the Z coordinates are 0. Select the new shape string created, come to the sidebar properties, placement position Z, where we can put in the equation to bring up the text right to the top. Maybe we can adjust the X and the Y positions. Come down further to the bottom, click the size and link it to the spreadsheet's font height property. And one text is almost ready. But let's copy it one more time for another text. Uncheck the spreadsheet so that it's not copied. Rename all the texts so that they are descriptive. Once we select the new text, come to the sidebar and change the placement position or the string name to PPS this time. Similarly, I created the last text, which was the project name. And we are ready to create pockets. Click the pocket tool and immediately we will see that it gives an error because these texts need to be part of an active body. So that's when we go hunting down our nested structure to find that body of the case. After finding the case body, make it active by double clicking it. Then drag each of the texts one by one inside the case. Now when we choose the text and click the pocket tool icon, there will be no errors. Instead, a sidebar will open up where we can put the length of the pocket. Click the blue circle icon and link it to the text extrude alias name from the spreadsheet, which is basically half of the wall thickness. And voila, we see the little pocketed text. Repeat the same process to create the pockets for others. Disable the case view with the spacebar, change its transparency, and we should be able to see the entire case with the text pockets. Slice it! This is the last step. I mean, really, thanks for sticking with me. Change to Part Workbench and click on the tool to create parametric geometric shapes. For simplicity, I'm going to create just a plane, which is the default option. A sidebar will open up to add the dimension and positions of this plane, but I always like to change it later. So click Create and close it. A tiny square plane is seen right at the bottom of the case. Drag the plane inside the part to keep things organized. Select select the created plane in the model view and start playing with the length, width, and placement positions in the sidebar. The length will be the entire case, plus I extended it out on both sides because we have to eventually ensure the separation plane makes a clean cut of the entire case. In position X, I will put a negative of extend out so that it's symmetrical. I do something similar with position Y, but the presence of the screw lugs means that we need to extend it out even more. And finally, I changed the width to also cover the entire case. Rotate it around and make sure the separation plane is covering everything. Now we need to bring up the plane along the Z-axis. So edit the equation to add wall thickness plus clearance plus height of the PCB from the bottom, because that's where I decided to slice the case. Do zoom in and check that it's in the correct position, especially the connector slots. I wanted it to cut right below the PCB. Once we are satisfied, select both the fused case so far and the separation plane and go to the menu Part, Slice, and Slice Apart. A new object will be created called Exploded Slice. Drag it inside the part case, expand it to see Slice 1 and Slice 0. Press the space bar, disable the view of both the slices and maybe even the PCB. Enable the view of Slice 0 and rename it accordingly, which is the bottom of the case. Maybe change its transparency to have a clearer view. Then enable the visibility of the other slice and rename it to top and change the transparency as well. To truly see it split, select the top, come to the sidebar at the bottom, placement, position Z, and increase it. Enable the visibility of the PCB, and finally, I was so relieved that it's done. But we are not quite done yet until we prepare it for 3D printing, right? Disable the view of the PCB and the top, select the bottom, go to File, Menu, Export, STL Mesh File extension and name it as bottom.stl. Similarly, disable the bottom view, enable the view for the top of the case, go to the menu File, Export STL Mesh and type in top. Once we view the folder where we saved the STL files, we should be able to see them. How do we view these STL files? On Mac OS, simply double-click it and it should open in the Preview app automatically. Rotate, pan, and zoom to have a good view of the file. On the web, there are a few options. If you have uploaded the STL file to GitHub, there is already a native viewer with 3 different options like the wireframe, surface, angle, and solid. Otherwise, do a quick search online. I did like the first search result as well, where we can simply drag and drop the STL file to view. So there are plenty of options to view and check everything is fine before we head to the 3D printer. I don't own a 3D printer, so having something online is a great convenience. I decided to try PCBWay's 3D printing online service. Once we are on the 3D printing order page, we can simply drag and drop all the relevant STL files. It will immediately give a cost based on the dimension and material. Since this was my first time, I kept it at the default settings of using resin as the cheapest material that I wanted to try. After I submitted the request, it was under review for less than an hour, and after that I could proceed to pay for the cost of $24 and shipping. I think I ordered it on Monday morning, and by Friday afternoon, DHL delivered it to me, and that was really fast, within a week. So why don't we put it all together now? And to do that, I chose screws, specifically something called self-tapping screws, because as we designed, my screw lugs did not have any threads. So I bought these self-tapping screws online with the required height. Thankfully, there are so many options. The most common question on using these self-tapping screws is, what is the pilot hole size? It all depends on the material used. The softer the material, the smaller the pilot hole. But all pilot fillet holes are smaller than the actual hole, which is M3 in my case. So I bought an M2.9 self-tapping screw and used 2.8 as the internal screw lug diameter. Does it work with the resin material that I printed? Yup, it works, but it's a lot of hard work. I used 6 screws of 20 millimeter length, and cutting each of their threads into the plastic material was tougher than I thought. I took 15 minutes for only 6 screws, and I can still feel my right biceps. So definitely for my future projects, for my future design, I'm going to take note if it requires that long to cut the threads. And this brings me to so many other things that I should not be doing in my next design. On one hand, I'm really excited that I got it done. This is my first case and it does work. And on the other hand, I am unsatisfied because I can see so many things that I can improve. The first improvement is that probably I'll never be able to design a PCB without a case in mind. And this includes routing the traces, connector, and the LED positions in such a way that it appears symmetrical and pleasing in design. Secondly, I'll probably never go for such a long wall, especially with resin material, because it curves slightly with a 1 millimeter wall thickness. Next, definitely wider ventilation holes with more spacing in between them so that the material does not bend. As for the connector slots, I went with ample clearance on all sides. I guess I can be braver to reduce the clearances and try more shapes like rounded corners and trapezoid. I also want to try a separation plane that is not just a straight line. This will give me the flexibility to split the case exactly where I want to. And lastly, maybe try a snap fit enclosure that will eliminate all screws and save on the bill of materials. I admit I was intimidated at first because there is a learning curve to learning this thing. But now that I have finished my first case, I feel like an entire whole new world has opened up for me. And not to mention, I always hear parents raving about 3D printing stuff for their kids. So let me know your ideas on that. I'm sure my 2-year-old will be excited. What type of features would you like to include in your electronics enclosure? Let me know in the comments down below. Lastly, for those of you who are like me before, are also thinking of making your first electronics enclosure, may the beginner's mind of openness, eagerness, and perseverance be with you. Thanks for watching and see you next time.